section 3.3, we talked a little bit about concavity. Within concavity, we have the discussion here, we have to talk about the second derivative. And that's basically all the real thing that we got into here was just discussing what the second derivative is. The second derivative is a derivative of the first derivative. So if you can do it once, you can do it twice. It's really what we're talking about here. Let's look then at this one, our definition of concavity. In order to do that, let's take the inspires, and I'm going to give you a function. And we're going to look at this function, x cubed minus 5x squared plus 4x. And we're going to change the window a little bit. So I'm going to use a window setting of -2 by up to 5 on the input. We'll scale it by 1. The outputs, I want to use -10 to 5, and we'll scale that by 1 also. So we've got -2 to 5 and -10 to 5. Okay, that should give us a nice looking graph. Now, I'm going to make a copy of this and put it in the notes so I can write on it. You, at the same time, can just kind of look at what you've got there and manipulate it as need be. But let me just put it right here for us. So again, mostly what we took care of on Tuesday was just looking at second derivative on this section. On this section, on today's lecture for this section, what I want to do is, I'm going to take this, and I'm going to move this right about here. Okay? Just part of the graph. Now, as seeing part of this graph, I want you to just kind of share with me everything you know about this function. And try to relate it to what we've talked about in section 3.2, 3.1, and so forth. For what you see here, yes?
Oh, sorry.
Aaron? No. We haven't talked about that in section 3.2 and 3.1. Okay, so let's save that. We're going to get to that, but just not yet. Yeah, Brian. Okay, it's increasing in part of it, right? Yeah, somewhere in here. Okay, so we have an increasing function. Good. What else? Yes, Aaron. For what we see an absolute. Let's just take out the absolute and just say we have a maximum up here. Because truly on the whole function we wouldn't call it an absolute. So we'll just fill out those terms. But we know it's a maximum because we can see it. I'm going to ask you a question more about that later. Anyone else? Increasing here. Maximum here. Yeah, Connor? Okay, so we're kind of keying in on this value here. It may be 1/2. We can kind of put a 1/2 there or not. So we'll say that's a critical number of the function. Let's be real specific about that. It's a critical number of f of x. I'm trying to have you think, if this is increasing here, can you give me a comparable statement? Decreasing on the other side? Okay, that's an important idea, by the way. It's an important idea. Now, we're talking about this. The only thing that we really have discussed that brings us into section, I think it's 3.2 in our textbook, is the fact that we have a critical number. I think that's where we first started talking about critical numbers. I could be wrong, but it's in there. How do we know it's a critical number? What did we do analytically to see that this was a critical number? Okay, so it's the derivative 0, so I'm going to put down that it's a 0 of the derivative. In other words, the derivative f prime of x is equal to 0. That's at this point right here. Okay. Now, the fact that the derivative is equal to 0 tells us what about the function, or about the graph? The slope of the line tangent to the curve at that point is, so a line that's 0, of course, is a horizontal tangent line. Okay, good. So let's go back to this. We say that the function is increasing. How does that relate to what we talked about in section 3.2 or so? In other words, where's the calculus in the fact that this is increasing? Okay, which means that the derivatives along this, in the same area, the derivatives are what? Positive, okay. And if they're decreasing, we'll just kind of put that up here. If they're decreasing, it means that the derivatives are negative. Now, there's something very significant about this critical number of the function, this maximum here. That maximum is a point, that value, that critical number of the function is a point where the function changes direction. It changes from being increasing to being a decreasing. From going uphill to, a little button on this pen, okay, from going uphill to going downhill. So this, all of this work then, we can say that the, at this critical number, at the 0, at this, let me do something better than that. At this critical number where we have this extrema, this is where the function changes direction. Now, that's an important idea. The function changes direction. It changes from being increasing to being decreasing, from going uphill to going downhill. When we have the first derivative equal to 0, we have a critical number of the function and so forth. Are we guaranteed that it's always going to be a maximum? All we know is that it's a possible extrema. Okay, I'm just looking at a portion of this. Now, who was it over here who started to tell me something else? I said, let's hang on to that just for a moment. Was that you, Aaron? Okay. Aaron, you wanted to tell me it's what? If I just look at this portion of it, yes, I would say that this half of it, somewhere right about here, is where I have this shade. But it definitely looks like the function is concave down. I think we talked about this also on Tuesday. My visual of concave down is coffee cup down. I see a negative connotation with that if it's upside down. If it's upside down, and all the coffee falls out of my coffee cup, there's also something very positive about it when I look at this graph. If the curve is concave down, I many times think of a maximum as a positive item. If I want to maximize my grade or maximize my income, that we often think of maximum as being a positive idea, but yet we find it when we have something that's concave down. And so the fact that the curve is concave down creates this positive idea or this maximum idea here. Okay? Here we go. Cover that up. Open it this direction. I'm going to open it just to about, where did I go? Right about here. Discuss this curve with me. Same type of discussion we could have. We have another extrema, right? It happens to be a minimum now, but it's an extrema. Now, I see that the left side of that extrema, this one is now decreasing, but what's the calculus of this? If it's decreasing, we can determine that by what? Which means that the derivative is negative. Okay? Increasing on this side. So we would then say, well, that's where the derivative is positive. At this minimum, You have a critical number of the function. What else do you have? Yeah, you've got another 0 of the first derivative. Okay? Is this a point also where we're changing direction on this curve? It goes downhill and then it changes direction and goes uphill, decreasing then increasing. Okay? So we can have a similar discussion, and now we talk about the concavity of this. It's not concave down, it's concave up. Okay, so again, the visual that we can use is coffee cup up. And because we have a concave up, it has created what may seem to be a negative thought in our head. If we think about the minimum of something, a negative. But definitely there is that connection between the fact that we have this concavity, this concave up portion. Now, what's interesting then is that this is the same curve as we just saw. It's the very same curve, and there is some point right here, some point where what happens? At this point, what's happening on the curve? Yeah, Philip.
Inflection point, so the concavity is changing.
Okay, that's from don't give me the first part just yet, but the second part I want. This is where the function changes concavity. And that's a very important point to us. A very important point in our discussion of work. We need to know where does the profit or revenue or demand or cost, where does it begin to change in its growth or decay? What happens? Well, right here's a very important piece right there. Now, Philip also gave us at that point, we would say that this value right here, or this point, is an inflection point, and that's exactly what we call it. Correspondingly, on the blue writing, that very special point, it wasn't a point of inflection point, but it was an extrema. And so this point of inflection is equivalent in our thinking, in our work, to what the minimum is to the first derivative. So, let me say that again. The inflection point has the same importance to us as a minimum or a maximum in extrema. So how do we go about finding the minimum in extrema? We set the equal to, did you fill in the blanks for me? We set the first derivative equal to 0. So what do you think we're going to do to find that point of inflection? To find that point where concavity changes? We're going to find a critical number of something by taking or locating what? We're going to use the second derivative. What about the second derivative? Yeah, we're going to find zeros of the second derivative. Didn't we find extrema by taking zeros of the first derivative? And those became critical numbers of our function. So if we take zeros of our second derivative, we have found critical numbers of our first derivative, and those critical numbers will indicate possible, we should put the word possible up here, possible inflection points, just like the zeros of the first derivative find possible extrema. They're not always extrema. They could be something else. Okay, so now this is what we're doing. This is the whole gist of what we're about to do in this whole section, is analyze the concavity of a curve by using the second derivative, and that's why we have to know what a second derivative is. Well, let's go back up to the notes here. Definition of concavity: a function is differentiable on an open interval. If it's differentiable, it's also continuous. So